Welcome to The Explainer. Today we are talking about one of the most, mind-bending technologies in AI. It's a system that, for all intents and purposes, taught computers how to dream.
Okay, let's just start right here. I want you to take a really good look at this face. I mean, every detail, the way the light hits her eyes, the texture of her skin. It looks completely and totally real, right? Well, it's not. This person is not real. She has never existed. She is essentially a ghost in the machine, dreamed up entirely by an AI.
And that's the million-dollar question, isn't it? How on earth can a computer create something so convincing, so human, from absolute scratch? This isn't just some clever Photoshop trick. We're talking about pure digital creation. And the answer is found in this really clever machine learning framework that's all about a high-stakes competition.
All right, so the technology behind this magic trick is called a Generative Adversarial Network, or GAN for short. The whole idea was cooked up by a guy named Ian Goodfellow and his team way back in 2014. And believe me, it completely changed the game for generative AI.
You see, the real genius of a GAN is that it isn't just one AI working alone. No, it's two AIs, and they're locked in this constant digital battle. You can think of it like an AI arms race, where these two networks are just relentlessly pushing each other to get better and better.
So to really get this, let's use an analogy. Let's imagine a game between two absolute masters of their craft. You have a brilliant, world-class art forger, and you have an equally brilliant art detective. One's job is to create the perfect fake, and the other's is to spot it. It's a zero-sum game.
So, meet our two players. On one side, we've got the generator. That's our counterfeiter. Its whole goal in life is to take random static and try to turn it into a totally convincing fake image. And on the other side, we have the discriminator, our detective. Its only job is to look at a piece of art and make one call. Is this the real deal, or is it a fake that the generator just cooked up? Okay, so we've got our players on the board, the forger and the detective. So how does this game actually play out? And more importantly, how do they both get so ridiculously good at what they do? Well, it's all about this relentless feedback loop. The generator cranks out a bunch of fakes. Then the discriminator is shown a mix of real images and those fakes, and it has to guess. After each round, both of them get what's basically a report card. The generator learns what it did wrong on the fakes that got caught, and the discriminator learns from any fakes it missed. Now repeat that process millions of times. Each one is constantly sharpening the other.
So what's the end game here? Well, the goal is to reach a point called equilibrium. This is where the generator's fakes have become so unbelievably good that the detective, the discriminator, is basically just guessing. Its accuracy drops to 50-50, no better than a coin flip. And when that happens, you know the generator has truly mastered its craft.
But you know, this whole training process, it's a really delicate balancing act. It's high stakes. And if that balance gets thrown off, well, the whole system can break down in some pretty spectacular ways. Probably the most common way this goes wrong is a problem called mode collapse. And this is basically where the generator gets lazy. It finds a little loophole in the game, and it exploits it. Some people call this the Helvetica scenario. Think back to our art forger. Imagine he figures out that his fake $20 bills fool the detective every single time. So what does he do? He stops bothering with 50s or 100s and just starts printing those 20s over and over. The generator does the same thing. It might find one type of image that always works and just produce that, completely failing to learn the rich diversity of the actual data. Now, despite big challenges like mode collapse, researchers in this field, they don't give up easily. They have been working non-stop, creating what's now basically a whole zoo of different GANs, each one designed to be more stable, more powerful, and smarter than the last.
And the pace of progress has been just staggering. I mean, you go from the original idea in 2014 to just 3 years later, in 2017, we get progressive GANs, which figured out how to build stable, high-res images. Then, just 2 years after that, StyleGAN 2 comes along and starts making faces so real that you literally can't tell the difference.
And things like StyleGAN gave us this incredible new level of control. Suddenly, the AI could separate big picture things, like a person's pose, from tiny details, like their hair texture. This meant you could start to mix and match these features. It's kind of like a digital Mr. Potato Head, but for creating hyper-realistic people. So, with this explosion of progress, GANs are definitely not just a cool science experiment anymore. Oh no, this technology is out in the wild, and it is actively being used to create entirely new realities across a ton of different fields.
And the applications are, well, they're all over the map. In science, they're helping us simulate really complex physics. In medicine, they can create synthetic patient data so we can do research without violating privacy. In the art world, a portrait made by a GAN sold for almost $500,000. But there's a flip side. This is the exact same tech that powers deepfakes and those fake profiles you see online, which, opens up a whole Pandora's box of ethical problems.
So there's no question, GANs are a monumental leap forward for AI. It's a huge step in what we might even call creativity. But this power is a true double-edged sword. And as these networks just keep getting better, blurring that line between what's real and what's generated, it leaves us with a really big and kind of unsettling question. In the future, how will any of us really know what's real?